Hello and welcome to Tech Simplified TV. In our last episode, we have discussed about placement in VLSI physical design. After placement, it's time for routing. Routing is done in 3 different steps: global routing and detailed routing for optimization. And specialized routing is for those special nets which require extra attention. In today's episode, we will discuss about global routing and its different aspects like optimization goals, different techniques of global routing, finding shortest path, etc. If you are interested, stay tuned and stay focused till the end of the video. Now let's take a look at the pointers we are going to discuss in today's episode. First, design flow and global routing. Next, detailed and specialized routing. Today in this episode, we will discuss mostly about global routing, although detailed and specialized routing are another 2 types of routing. We will give a touch base on that. So this slide is about that. So this second slide is about touch base of detailed and specialized routing. And after that, essential terminology for global routing. Here we will learn some technical terms that is related to global routing so that in later slides when we discuss it in detail, we don't get stuck. After that, what is SwitchBox in routing? SwitchBox is another terminology that is introduced in routing, and there are 2D and 3D SwitchBox are there. So here in this slide, we will understand in detail what actually SwitchBox is. Next, optimization goals in global routing. After that, representing routing regions. Routing region is another new terminology. In this slide, we will discuss how routing regions are represented and global routing flow. So there are some sub-steps of global routing process. Here we will learn that. And next, single net routing, global routing in connectivity graph. Finding shortest path. There are 2 algorithms discussed here, Dijkstra's algorithm and A-star search. These 2 algorithms are discussed here. Next, full netlist routing, global router. This is not about any specific router. This is a generalized idea about a global router, how it works, what are the main components or methodologies used. And finally, optimization for different design types, full custom, standard cell and gate array. So these are the pointers we will discuss in today's episode. We are done with this slide. We will move to the first slide. Design flow and global routing. This is the infographics we are using in the episodes based on backend. VLSI design flow starts with system specification, then architectural design, functional design, logic design, circuit design. After that, physical design. Once we get the synthesized netlist, after that, whatever we do, that is part of physical design. And physical design is not a single step. There are partitioning. We have done placement as a part of chip planning, flow planning, and ground and power pin routing. That is also done. Clock tree synthesis. We have an episode on clock tree synthesis and another episode on what is clock tree. We have both episodes to give a good idea about clock tree and synthesis of clock tree. And now signal routing. So signal routing has 3 steps: global routing, detailed routing and specialized routing. In this episode, we are concentrating on these global routing. So in VLSI, routing is a crucial step that connects the various components like logic gates, transistors and memory cells on a chip. It involves determining the paths for electrical connections which are implemented through metal layers on the chip. In partitioning, area is partitioned. In placement, modules are placed. Now they need connection. How that is done, that method is called routing. So it involves determining the paths for electrical connection which are implemented through metal layers on the chip. And routing is divided into 3 major steps: global, detailed and specialized routing. Global routing is basically the initial stage of routing. Detailed routing is more detailed, and in specialized routing, special signals like clock signal taken care of. Global routing, initial stage of routing process where the chip's overall routing framework is determined. It defines the general paths for each connection or net without focusing on precise details. The goal of global routing is to create an approximate plan for how the nets will be routed across the chip. That is global routing. It's the initial step. And what are the key aspects of global routing? Calculates the approximate net paths and assigns them to regions or grids within the chip. Allocates appropriate create metal layer for detailed routing without specifying exact geometry, prevents congestion by ensuring sufficient routing space for all nets, divides the chip into grids, systematically determining regions for each net, focuses on optimizing overall interconnection layout rather than precise routing geometry. After global routing also, there are quite a good scope of improvement, and that is done in detailed routing. Global routing is the initial stage. Here we decide the framework, allocates metal layers although doesn't specify the exact geometry, try to prevent the congestion by ensuring sufficient routing space for all nets, divides the chip into grids systematically just to keep the region for each net, and optimizing overall interconnection layout rather than precise routing geometry. So that is the overall key aspects of global routing. We are done with this slide. We will move to the next slide. This episode is dedicated for global routing. Since we have mentioned, we are giving a touch base about detailed and specialized routing. In later episode, we will discuss these two types of routing in detail. Detailed routing, this stage refines global routing into precise manufacturable paths, finalizing the layout of electrical connections for fabrication. Key aspects of detailed routing. Detailed routing defines precise wire paths while adhering to design rules, including spacing, width, via placement, and metal layer usage. It optimizes vias, ensuring signal integrity by minimizing RC delay and crosstalk, and resolves congestion by redistributing wires or using alternative layers. Special attention is given to power and ground routing to guarantee reliable voltage delivery across the chip. These are the key aspects. What it does, it defines precise wire path while adhering to the design rules. It strictly follows the design rules. Design rules are set by the fab lab, that fabrication unit. We have to follow it. Whenever design is there, before tape out, DRC clearance is absolutely necessary. Otherwise, the design or the GDS2 is not manufacturable. These are the bare necessary geometry that is mentioned here, and we have to adhere by that. In detailed routing, it follows strictly design rules, including spacing, width, via placement, metal layer usage, everything. All data are there, the strict rules are there, and it follows these rules. This optimizes vias, ensures signal integrity by minimizing RC delay and crosstalk, and resolves congestion by redistributing wires using alternative layers. Special attention is given to power and ground routing to guarantee reliable voltage delivery across the chip. And now specialized routing. Specialized routing handles net with specific requirements such as clock, power network, high-speed signal, ensuring they meet performance constraints. So special net, special care, and specialized routing. Key aspects of specialized routing. Specialized routing includes critical net and clock routing, ensuring precise timing and reliability. It also covers power and ground distribution, high-speed signal routing, and shielding for noise reduction. This ensures optimal performance and signal integrity in complex design. So these are key aspects of specialized routing. So here, that much we are discussing about detailed and specialized routing in this episode. In later episode, we will discuss these both topic in detail. So we are done with this slide. We will move to the next slide. Essential terminology for global routing. So these are the some important terminology. We will use them later. So let's try to understand what it means. A routing track. A routing track represents a horizontal or vertical wiring path that facilitates the routing of signals. Signal net traverse these paths by alternating between the horizontal tracks and vertical columns connected using interlayer vias. So it's talk about routing tracks. This diagram shows horizontal routing channel. This area, if cells are there, standard cells are there, this area is highlighted here, how these look like. So routing region. A routing region is a defined area containing routing tracks or columns. It serves as the guide for allocating wiring paths to connect signal net efficiently. So a routing region is a defined area containing routing tracks or columns. It serves as the guide for allocating wiring paths to connect signal nets efficiently. So routing track and routing region. Now uniform routing region. This region consists of evenly spaced horizontal and vertical grid lines forming what's known as global grid or grid. The grid comprises unit cells called global cell or G cells. Typically, the spacing between grid line ranges from 7 to 40 routing tracks, balancing the complexities of chip scale global routing and detailed routing task. Non-uniform routing region. Unlike their uniform counterparts, non-uniform regions are defined by boundaries aligned with external pin connections or macro cell edges. That region includes channel and switch boxes of varying dimensions. Now channel. A channel is a rectangular routing region designed to connect pins located on its two opposite sides. While the other two sides remain pin-free, channels are further classified as horizontal channel, vertical channel. Features pins along the top and bottom boundaries, and vertical channel features pin along the left and right boundaries. So horizontal channel pins are above and below, and if the channel is vertical, obviously that will be on the both sides, that is right and left boundaries. G cell or global cell. Global cell or G cells are the fundamental units within global grid. They serve as basic building blocks for defining paths in routing regions and are instrumental in routing process. So these are the terminology: routing track, routing region, uniform routing region, non-uniform routing region, channel, that is horizontal and vertical channel, G cells or global cells. These are the important terminologies. We are done with this slide. We will move to the next slide. What is switchbox in routing? A switchbox is a square or rectangular region where multiple channels intersect. This critical structure enables connections between different routing tracks or columns, enhancing the routing network's flexibility. So switchbox is basically a junction. Multiple channels intersect. That is a switchbox. Here it's shown switchbox routing between horizontal and vertical channels of a macro cell. In this region, both vertical, this is horizontal channel, this is vertical channel, they meet, and in all sides the routing is done. These interconnects are traveling from one side to other side. A 2D switchbox exists in a single plane. In this plane, that is a 2D switchbox. A 2D switchbox exists in a single plane and connects horizontal and vertical routing channels within the single metal layer. It serves as a connection hub in a single metal layer, because in a chip, if that is the cross section vertically, like these multiple layers of metals are there and vias are vertically connected, connecting one layer to another, like that only. And for a 2D, and it's basically 3D on, I don't know whether you can understand my drawing. This way. These vias are vertical on any plane, any horizontal plane, and in a 2D switchbox that is in one single plane, it exists on a single plane and connects horizontal and vertical routing channel within that single metal layer. It serves as a connection hub, enabling routing. I said it's like junction. It serves as a connection hub, enabling routing paths to switch directions, that is horizontal to vertical or vice versa, within a specific routing layer. In a specific routing layer means in specific metal layer or a specific plane. Frequently used in PCB design or simpler VLSI design where interlayer routing is minimal or non-existent. The region typically resembles a rectangular or square grid with intersection points for connecting different channels. A 3D switchbox. A 3D switchbox incorporates connection across multiple layers of a chip, often through interlayer vias. It facilitates interconnections not only between horizontal and vertical tracks but also between different metal layers. This capability is crucial for modern multi-layered ICs. This is shown as a 3D structure, metal 5, metal 4. So here if we consider it's a 3D switchbox. It facilitates interconnection not only between horizontal and vertical tracks but also between different metal layers. This capability is crucial for modern multi-layer ICs widely used in advanced VLSI designs where chips have multiple layers of metal routing such as in 3D ICs or multi-layer ASICs. Extends the concept of 2D switchbox to include vertical pathways allowing signals to traverse different physical planes within the chip. That is 3D switchbox. So we are done with this slide. We will move to the next slide. Optimization goals in global routing. Minimizing total wear length, managing routing congestion, maximizing timing slack, balancing via usage, optimizing for power efficiency, adapting to design constraints. So these are the optimization goals. So minimizing total wear length, that is the first one. Wear length minimization is fundamental goal in global routing or any design because reducing the total wear length enhance performance, heat is less, signal will travel less path, so delay will be less. Shorter wears reduce signal propagation delay leading to faster circuit. Less wear wire length means reduced capacitance and consequently lower power dissipation. Shorter interconnects decrease the chances of defects and increase manufacturability. Managing routing congestion. Congestion arises when multiple signal nets compete for the same routing sources. Effective congestion management ensures efficient resource utilization, prevents overloading specific regions while underutilizing others, avoids unnecessary detours that can increase wire length and delays, reduces the risk of violating constraints such as spacing between wires. Maximizing timing slack. Timing slack refers to the difference between required arrival time and the actual arrival time of a signal. Maximizing timing slack is crucial for meeting timing constraints. That ensures that all signals arrive within their designated time windows, provides a buffer against variations in manufacturing or operational conditions. So, time slack is required for meeting timing constraint. So, that ensures that all signals arrive with the designated time windows, provides a buffer against variation in manufacturing or operational condition. And balancing VI usage. VIA connect different metal layers in a chip's layout. Excessive VIA usage can increase manufacturing costs, lead to reliability issues due to thermal stress and delays by introducing additional resistance and capacitance. Balancing VIA usage is therefore vital for cost-efficient and reliable designs. Optimizing for power efficiency. Power optimization is critical, especially for portable devices and data centers. Efficient global routing minimizes dynamic power by reducing switching activity and interconnect capacitance, minimizes static power through efficient use of routing resources to minimize leakage. And now adapting to design constraint, modern VLSI design face constraints like fixed die boundaries, specific routing resources, and predefined placement. Optimization ensures that these constraints are respected without compromising the overall design quality. So these are the optimization goal of global routing. Now we will move to the next slide. Representing routing regions. In global routing, channels and switchboxes are represented as graph, where nodes represent routing regions and edges represent adjoining region. There are three graph techniques. One is grid graph, second is channel connectivity graph, third is switchbox connectivity graph. So this is the layout and its grid graph representation. It's divided into equal grids and each grid cells are numbered 1, 2, 3, 4, 5 like that. So also defined as global grid or G grid. A uniform grid overlays the chip layout. It consists of horizontal and vertical grid lines that divide the chip into smaller cells known as global cells, and grid lines are fixed at regular intervals to balance global and detailed routing complexity. That is grid graph. Second is channel connectivity graph. Graph that is function of V and E, where nodes V belongs to capital V represent channels and the edges E represent adjacencies of the channels. Capacity of each channel is represented in its respective graph node. So the same design, these are the channel and these are the free zone, the channels. 1, this is second channel, this is third, 4th, 5th, 6th, and now connection is like that. So 1 to 4 can be done through this way and 3 to 4 is connected, 3 to 8 is connected this way. That is layout and channel connectivity graph. And now switchbox connectivity graph, where these nodes V represent switchboxes and each an edge exists between two nodes if the corresponding switchboxes are on the opposite side. So switchboxes, the nodes represent switchboxes. These are the nodes. Nodes represent switchboxes from where it's crossing, like this way and that way. That one crossing, that's one second crossing, third crossing, that could be a crossing, that is another crossing from here and there, that is crossing of these and that, 2 to 6 and this way. It's all crossings. So switchboxes, and an edge exists between two nodes if the corresponding switchboxes are on opposite sides of the same channel. This is a channel and these opposite side of same channel, and the edge between these two that is connected when an edge exists between two nodes. These two nodes, if the corresponding switchboxes, this one switchbox and these two switchbox, they are situated just opposite to each other. That is switchbox connectivity graph. These are three representation: grid graph, channel connectivity graph, and switchbox connectivity graph. So we are done with this slide. We will move to the next slide. So global routing flow. Okay, so first is defining the routing regions, and there are some steps like partitioning the layout area into routing regions, allow nets to be routed over standard cell in some cases, and structure the routing region as 2D or 3D channels, switchboxes or other region types. Now represent the region along with their capacities and connections as a graph. Now step 2 is mapping nets to the routing region. Provisionally assign each net in the design to one or more routing region to connect all the pins. Now ensure the number of net passing through routing region does not exceed its routing capacity. Consider timing and congestion as factors influencing the path selection for each net. And third is assigning cross point. Assign routes to specific spots or cross points along the edges of routing areas. Align cross points to simplify handling design with millions of cells. Enable faster processing through parallel and distributed methods by allowing independent work on each routing area. Analyze the dependencies between net connections and the order of routing channels to optimize cross points assignment. These are 3 steps by which global routing flow is done. So we are done with this slide. We will move to the next slide. Single net routing. A set of pins that electrically connected is called net. A single net routing task deals with routing one such net at a time, ensuring it adheres to design rules while optimizing for factors such as wire length, timing, and congestion. For a 2-pin net, the task is relatively straightforward, requiring a path between the 2 pins. For a multi-pin net, the net is decomposed into smaller 2-pin subnets before routing. So, objectives of single net routing is minimizing wire length, reduce the total length of the wire connecting pins, minimizes delays and power consumption. Adhere to design rules, ensure the route meets constraints like spacing, wire limits, and layer assignment, and avoid obstacles, navigate around fixed blocks, macros, and other routed nets. Optimize timing. Critical nets must be routed with minimal delay to meet performance requirements. So these are objectives of single net routing. Now techniques for single net routing. Rectilinear spanning tree. A rectilinear spanning tree connects all terminals, that is pins, using only direct pin-to-pin connections with vertical and horizontal segments. These connections are restricted to meet exclusively at pins, meaning that crossing edges do not intersect and no additional junction points are introduced. When the total length of the segment is minimized, it's called rectilinear minimum spanning tree, that is RMST. It's a direct pin-to-pin connection. There is an example, P1 to P2, it's a direct connection, and P2 to P3, another direct connection. Otherwise, P1 to P2 can be connected like this, and P2 to P3 is straight like that only. And rectilinear stainer tree, that is RST, that is a little bit different. A rectilinear stainer tree connects all pin locations, and many include additional locations called stainer points, this one. While any rectilinear spanning tree for a P net qualifies as an RST, introducing strategically placed stainer points can often reduce the total net length, and RST becomes a rectilinear stainer minimum tree, that is RSMT, when the total length of the segment used to connect all pins is minimized. Like from P1 to P2, if we introduce one stainer point, from there only we can draw this another connection, like P1 to P2 through S1, and from S1 it's connected to P3. These are rectilinear spanning tree and rectilinear stainer tree. These are techniques for single net routing. We are done with this slide. We will move to the next slide. Global routing in connectivity graph. Global routing using a connectivity graph that is done by following different steps like defining routing region, defining the connectivity graph, determining the net order, assigning tracks for all pin connections, and global routing of all nets. So these are the steps. The vertical and horizontal routing regions are formed by stretching the bounding box of all cells in each direction until a cell or chip boundary is reached. So if these are the region of a cell, so from here in the next diagram we can see that there is it's stretched like that. From here it's stretched like this. From here it's stretched like this way. Defining the connectivity graph. In connectivity graph, nodes represent routing regions, edges indicate their continuity, and each node stores the horizontal and vertical capacities of its region. So in this way, horizontal and vertical macro cell edges are extended to form the routing region. So routing regions is defined. Now routing regions is represented by routing graph. So this is a defined one, the same design, the same layout actually, and now it's converted into a vertical capacity, horizontal capacity are mentioned with the nodes. So each node stores the horizontal and vertical capacities of its region. So this way it's represented as a routing graph. Now determining the net order. The order of of net processing can be set before or during routing based on factors like criticality, pin count, bounding box size, that is larger gets higher priority, or electrical properties. Some algorithms adjust dynamically based on layout characteristic observed during routing. Now, assigning tracks for all pin connection. A horizontal and vertical track are reserved in each pin's routing region to ensure connectivity. And final, global routing of all nets. Each net is processed sequentially involving steps such as net or subset ordering, track assignment using maze routing algorithm, and capacity updates in the connectivity graph. Substeps through which global routing is represented in connectivity graph. So we are done with this slide. We will move to the next slide. Finding shortest path, Dijkstra's algorithm. This algorithm finds shortest path from source node to all other nodes in a graph. Work with graphs that have non-negative edge weights commonly used in maze routing and shortest path problem. So this non-negative edge weight is a prerequisite of this method. About parameters, graph with non-negative edge weights, source node is as the starting point and target node as the destination. Node groups, there are 3 groups. Group 1 or unvisited nodes. So nodes that have not been visited is unvisited node and grouped as a group 1, and next group 2 is considered nodes. Nodes is visited but shortest path cost not finalized, and group 3 is known and finalized, like nodes for which the shortest path cost is determined, that is in group 3, third group. So optimization objectives are geometric distance, routing congestion, electrical properties, and weight densities. These are the optimized objectives. And algorithm initialization, all nodes starts at group 1. The cost of reaching each node is to set to infinity except for the source node which has cost 0. That has a cost 0. This is the source and this is the target. The cost of reaching each node is to set infinity, and except for the source node is 0. Parent of each node is initially unknown. The source node is moved to group 3 as the first known node. Value set to is 0 and its cost is known. So we will first move it to third group, that is known nodes. From there, we will start to solving the problem. The algorithm execution while the target node F is not reached. Compute the cost of reaching neighboring nodes from current node. So from A, we can move either towards D or towards B. If we move towards D, the cost is 1, 4, and if we move towards B, it's 8 and 6. Less costly path is A to D. So we will consider this one. This is the first we will consider. A will move to group 1 and A, parent of D, this will move to group 2. If node is already in group 2, compare and update its cost. If a better or lower cost path is found, select the lowest cost node in group 2 and move it to group 3. Repeat until the target node is added up to group 3. This is the method. In next slide, we will see how we can do it. So these are the prerequisite knowledge we need to understand Dijkstra's algorithm, like input parameters, node group, optimization, objective, initialization, and execution, how it's done. So we are done with this slide. We will move to the next slide where we will discuss how we can do it. So path reconstruction, first A to D. A is first moved to group 3 and now A to D. A to D is 1, 4, A to B, 8, 6. So we will move this. This is the short, in between these two, this is shortest path or least costly path. So it will move to here. From D to G, if we want to go, it is 8, 8, D to G 8, 8, although the previous value will get added. So it will become 8 plus 1, 9 and 8 plus 4, 12. Look, D to G, that is 9, 12. We keep it here only. Now here let's try to go from this side. A to B, that is 8, 6. That is known. So A, B, 8, 6. Now from B to E, value of B is 8, 6. That is getting carry forward. B to either we can move from B to E or B to C. B to E would be 8 plus 2, 10 and 6 plus 6, 12. Another one is B to C is from here, this is the cost, and from B to C, that is 8 plus 1, 9, A 6 plus 10, 6 plus 4, 10. B to C, 9, 10. Obviously, this is most costly, so we will keep it and it's not accepted. And from D, there are two paths. We will move to E, so 9 plus 1, 10, 7 plus 4, 11. And from D to G, that is 8 plus 1, 9, 8 plus 4, 12, 9, 12. So D to E and D to G, lesser value is like D to G, 9, 12, not 10, 11. So A to D, now D to G. And obviously G to T is small. So this is the path. So D to E is as considered as this one, and A to B is also known. So we moved it to group 3. B to C is known and accepted. B to C 9, 10. Now E to F 18, 18, 12, 19, cost is increasing. So E to H and C to F, these are very costly. So we are not accepting it. Rather, G to H is 12, 14, G to H. D to G is 9, 12, and here it's 9, 12, and 9, 12 plus 3, 2, that is 9 plus 3, 12, and 12 plus 2, 14. This is a very small example of a graph. If we consider, so this is the least costly path. So we will move from S to T, that is A to H, through this path, A, D, G, H. Path reconstruction 1, F is found, backtrace from F to S using parent node to determine the shortest path. Efficiency consideration, each iteration only consider neighbors of the most recently added node, current node, reducing redundant calculation. Nodes move sequentially into group 3 based on the increasing order of their shortest path. The algorithm stops when the target node is added to group 3, ensuring an optimal path. Handling node cost, when nodes have traversal cost, each node is replaced by d-click, a complete subgraph of d. Click edges have weights equal to the original node cost. The original d incident edges are connected to different click nodes. This transformation ensures that path traversal accounts for node traversal cost efficiently. So this is the method. We keep on adding the value of the previous edge to the next node, and this way we go, because it's get added. Once we start moving, it's get added. So this is the least costly path. We will accept this one. We are done with this slide. We will move to the next slide. That is A star search. So finding shortest path, A star search. Similar to Dijkstra's algorithm but extend the cost function. Includes an estimated distance from current node to the target, guarantees the shortest path if path exists. The estimated distance should never exceed the actual distance. Admissibility criteria are efficient compared to Dijkstra's algorithm, expands only the most promising nodes, best first search. Reduce the solution space comparing to Dijkstra's algorithm. A tight lower bound estimate can significantly improve runtime. Can be derived from Dijkstra's algorithm by adding distance to target estimate and node priority to determine by sum of cost from start node like Dijkstra's level. Estimated remaining distance to the target. Bidirectional A star search is a variant, expands nodes from both source and target until region is met. Reduces the number of nodes considered slightly. However, tracking the order of visited nodes along with complexity of implementing an efficient solution poses significant challenges. In practice, these difficulties can outweigh the potential benefits of bidirectional search. This is another method. It's quite similar to Dijkstra's algorithm but extend the cost function. And there is one bidirectional variant of this A star search. Their nodes are expanded from both source to target until they meet each other. Whenever bidirectional method is there, so there always need to keep a track of the visited node. Along with complexity of implementing an efficient solution poses significant challenges in practice. These difficulties actually outweigh the potential benefits of bidirectional search. Methods of full netlist routing. There are two methods, integer linear programming and rip-up and reroute, that is RRR. A linear programming is a mathematical problem that includes a set of conditions called constraints and an optional goal or objective function to maximize or minimize. Both the constraints and the objective functions must be written as linear equations or inequalities. If all variables in linear program only take whole number values, it is called an integer linear program. When these variables are restricted to only 0 or 1, it's referred to as 0-1 ILP. There are various software tools like GLPK, Cplex and Mosaic that can solve linear programs. The ILP takes 3 inputs and width by height routing, grid G routing edge capacities, and the netlist. The ILP uses 2 sets of variables. The first set includes k boolean variables, each representing an indicator for one of k specific paths or routes for a net in the netlist. The second set contains k real variables, each of which represents a net weight for a specific route for a net in netlist. That is integer linear programming. There are some tools, various software tools who can solve integer linear programs and repub and reroute. Modern ILP solver can handle hundreds of thousands of routes efficiently, but commercial EDA tools require faster and more scalable methods. The repub and reroute framework addresses these by focusing on problematic nets. When a net faces obstacle or interference, RRR temporarily allows violations route all nets, then interactively removes and reroutes some to reduce conflicts. Alternatively, push and shove strategies move existing nets to new positions to resolve congestion or make unroutable nets feasible. A greedy routing approach avoids violations but often causes large detours. In contrast, RRR permits temporary overcapacity routing to optimize overall paths. Allowing violations and rerouting enables more efficient routing with fewer detours than strictly violation-free methods. In the RRR framework, not all violation nets are ripped up, reducing runtime significantly with only a small increase in well length. Alternatively, push and shove strategies may move existing nets to new positions to resolve congestion or make unroutable nets feasible. A greedy routing approach avoids violations but often causes large detours. These are two types of full netlist routing methods: integer linear programming ILP and repub and reroute, that is RRR. Now, global router. It's a generalized view of what a global router contains of. Global routing instance. Now, net decomposition, initial routing. If there is violations, then repub and reroute and go again for check for violation. If there is no violations, that will go to layer assignment and final improvements. So, a global router first divides multiple pin nets into 2-pin subnets and generates an initial routing solution on a 2D grid. If there are no violations, it assigns layers by mapping the 2D routes into a 3D grid. If a violation occurs, problematic nets are ripped up and rerouted iteratively until the design is violation-free or stopping conditions such as a CPU limit is reached. In the last slide, we have discussed how RRR works. A global router first divides a multiple net pin into 2-pin subnets and generates an initial routing solution for a 2D grid. If there is no violation, it assigns layers by mapping the 2D route into a 3D grid. If violation occurs, it only picks up the problematic nets that is ripped up and rerouted iteratively until the design is violation-free or a stopping condition comes. It only do for the problematic one. It's a case-specific thing. Some routers include an optional cleanup pass to minimize wear length after repub. Alternatively, some global routers route directly on 3D grid, which can improve wear length but is slower and may fail to complete routing. So nets are routed using maze and pattern routing with negotiated and congestion routing, managing cost. Global router determined path for 2-pin nets while adhering to capacity constraints, prioritizing minimal wear length. It employs maze routing methods like Dijkstra or star search to ensure the shortest path between points. However, these methods can be excessively slow, especially when topologies involve edges requiring minimal vias. Now, modern router implement RRR using negotiated congestion routing. In this approach, each edge is assigned a cost or value that represents the demand for that edge. Higher costs discourage nets from utilizing heavily used edges, indirectly encouraging them to explore alternative, less congested paths. So this is how a global router works. That is a philosophical representation of it. So we will move to the next slide, that is optimization for full custom design. A full custom design features a layout dominated by macro cells with irregular non-uniform routing regions. Key initial tasks include channel definition and channel ordering. Full custom design is dominated by macro cells with irregular non-uniform routing regions. Initial tasks include channel definition. Channel definition partitions the global routing area into routing channels and switch boxes. Channel ordering is determined using floor plan tree. If a part of floor plan cannot be represented using horizontal and vertical cuts, at least one switch box is used along with channels. Once all of the regions, channels and switch boxes are determined, the interconnects can be routed. So Steiner tree routing and minimum spanning tree routing are two methods used. Shortest path is determined by Dijkstra's algorithm. So this is the design. Now it's divided into regions represented by a graph. Now optimization for standard cell design. In standard cell design, when the number of metal layers is limited, feed-through cells are used to route a net across multiple cell rows. If the cell rows and netlist are fixed, the number of unoccupied sites within the cell rows is also fixed, which restrict the number of possible feed-throughs. As a result, standard cell global routing aims to ensure the design is routable and identify a low congestion solution that minimizes the total wear length. So these are feed-through cells. It's used when metal layers are limited. Feed-through cells are used for optimization of standard cell design. Next is gate array design. In gate array design, the cell sizes and routing region sizes, that is routing capacities, are fixed. Since adding extra routing resources is not an option to ensure routability, key tasks involve assessing the placement's routability and finding a feasible routing solution. Additional optimization objectives include minimizing the total routed wear length and reducing the length of longest timing path. So here cell size and routing region sizes are fixed. We cannot increase it. Comes in a package. Adding extra routing resources is not possible. So key task involves assessing the placement's routability and finding a feasible routing solution. What is available within that, we have to solve the routing issue. So additional optimization objectives include minimizing the total routed wear length and reducing the length of the longest timing path. So this is the optimization for gate array design. So we are done with this slide and we are done with our today's episode. That we had all for our today's episode. Thank you for watching up to this point. Don't forget to like, share and subscribe. If you have a question, put it as a comment. If you have a dislike, also put it as a comment. Thank you again and bye for today.